The diesel engine, now and into the future, a prime power source for the propulsion of smaller ships and the generation of electricity in larger vessels. Robust and dependable, the diesel engine makes a vital contribution to the operational efficiency of the Royal Navy. The secret of the diesel's ready acceptance is its low consumption of safe fuel oil. This it achieves with compression ignition. The four-stroke diesel engine works like this. During the induction stroke, air alone is drawn into the cylinder. The air is then compressed to a very high ratio, which raises its temperature to from 7 to 900 degrees centigrade. The fuel is then injected, igniting spontaneously to produce the power stroke. The fourth stroke exhausts the cylinder of the spent gases, which completes the cycle. It sounds simple enough, but with pressures inside the cylinder in excess of 2,000 pounds per square inch, introducing the fuel poses quite a problem. Furthermore, precisely the right amount of fuel must be injected at precisely the right time to match the load requirements of the engine. The dual task of feeding and metering the fuel is undertaken by the fuel injection pump. The performance and efficiency of the diesel engine depend very largely on the correct functioning of this relatively small component. Two types of fuel injection pump are used in the Royal Navy. This is the DPA rotary pump employed on the smaller engines. And this is the BPE inline pump used by the large engines. Separate BPE pumps may be employed for groups of cylinders. Now, starting with the inline pump, let's see how the very precise feed and metering of the fuel is achieved. The pump is powered by a positive drive from the engine and, on a four-stroke, rotates at half engine speed. A camshaft operates the plungers within the barrels, each plunger barrel unit serving its own cylinder in the engine. The pumping action is achieved in the following way. When the plunger is at bottom dead center, fuel under pressure enters through the barrel ports. As the plunger is pushed up, it blocks off the ports and traps fuel in the upper section of the barrel. The pressure in the barrel lifts the delivery valve. The fuel enters the fuel injector pipe and an equal amount is injected into the engine. When the plunger reaches the top of its stroke, a helical control slot uncovers the barrel port. The pressure is relieved. The delivery valve closes and injection ceases. By twisting the plunger in the barrel, the position of the helical slot relative to the fuel port can be altered, allowing the cut-off point and the amount of fuel to be controlled. This twisting action is achieved by a rack on the control rod operating a pinion to turn the plunger. A single rod controls all the plungers in this way, enabling the supply of fuel to be metered and timed accurately. But faults can occur which affect efficiency. Typically, these arise from congealed oil, incorrect assembly, leaking seals, and wear. So a knowledge of how to strip, repair, reassemble, check and fit the BPE pump is important if faults are to be identified and corrected. With the pump repaired and reassembled to the maker's instructions, the plungers must be retimed so that each one begins to deliver fuel at the exact angular interval between them in the firing order. This is being done on the hand phasing rig. By means of a tappet screw, the bump clearance of each pump element is set in the order of firing, again to the maker's specification. Now the cut-off point of each plunger is checked in turn by pumping through some fuel. The graduated disc is turned to 0 and the point of port closure rechecked before the delivery valve and spring are reassembled. Then, having ensured that all the elements are working correctly and uniformly, the phasing of the pump must be checked that it is correct. This is essential. Now, the pump must be calibrated to ensure that for any given position of the control rack, an equal amount of fuel is delivered from each pump element. In the workshop, this is done on the Hartridge machine, but hand calibration is also possible for repairs at sea. The pump is tested at a number of speeds and rack settings, the machine automatically displaying the output of each element. Incorrect calibration will lead to poor running and poor economy of the diesel engine. Any uneven deliveries can be corrected by adjusting the quadrant. When the pump has been refitted to the engine, it must be spill timed to ensure that fuel is delivered at the right moment in each compression stroke. The engine is turned to the point of injection for number 1 cylinder, confirming that it is on the compression stroke. The fuel supply is opened and fuel will flow from the gooseneck pipe. The pump camshaft is now turned in the correct rotation until the spill cutoff is reached. The engine pump drive is bolted tight to the pump camshaft. A recheck is made that the spill cutoff is perfectly in time with the point of injection marked on the flywheel. This should always be double-checked. When all the checks have been made and are correct, the engine will start and run. Now, the moment of truth. Right first time, which is as it should be. The worst that could happen with a single pump system is failure to start. But where an engine requires 2 or more pumps, the incorrect setting up of one of them can have catastrophic consequences. The dead cylinders are turned by the others, there's severe overheating within seconds, and the complete engine is destroyed. Many thousands of pounds down the drain and a ship disabled for many weeks. Yes, it has happened, and without due care and attention, it could well happen again. The correct performance of the DPA rotary pump is equally critical, if on a smaller scale. Let's see how it works. The operation of the DPA pump is different from the BPE pump. In it, a single metering chamber supplies all the injectors fitted to the engine via a distributor, rather like the electrical distributor on a petrol engine. The heart of the unit is the pumping and distributing rotor, turning in the hydraulic head. Plungers at the end of the rotor are opened by the pressure of the incoming fuel and then closed by cams to give the pumping action. When the inlet port in the head lines up with one in the rotor, Fuel is pushed into the pump. When the outlet ports line up, fuel is distributed to each cylinder in turn, the correct firing order being an integral feature of the unit. With its relative simplicity, the DPA pump is most unlikely to develop a fault. Stripping and reassembling are therefore not part of the syllabus, but setting up the points of injection, refitting and timing are. The back pressure test rig allows the components of the pump to be checked so that they are all operating within their design tolerances. The pump is back pressured and the drive rotated until it hydraulically locks and is sighted to ensure that it is on the correct alignment. Fuel flow with the shut-off control closed can be checked now. The maximum fuel setting can be measured and adjusted to bring it within the specified limits. Timing the pump to the engine is relatively straightforward, but the exact procedure must always be followed according to the type of engine. In all cases, timing marks scribed on the edge of the pump mounting flange must be accurately aligned with the timing marks on the engine. Whilst an incorrectly timed pump cannot damage the engine, it could result in failure to start. This could have serious consequences if the engine is required to fulfill its task in an emergency. Here, the pump is being primed ready for the first start-up after refitting. Small, compact and almost entirely trouble-free, the fuel injection pump holds a position of considerable importance. If poorly adjusted or wrongly fitted, it can bring a vessel or its equipment to a standstill. So the need to follow correct procedures cannot be overemphasized.